Figure 1 shows the satellite with 3 solar panels folded in close to the satellite's axis for the journey into space in the hold of a cargo spacecraft. Now we've got Figure 1 and Figure 2, and you can see those kind of retractable panels there. In Figure 1, they're closed in Figure 2, they're spread out. Just before it is released into space, the satellite is spun to rotate at 5.2 radians per second. Once released, the solar panels are extended as shown in Figure 2. So we've got the moment of inertia of the satellite about its axis with the panels folded, 110 kilogram meters squared, and then the same when the panels are extended, 230 kilogram meters squared. State the law of conservation of angular momentum. Now what I'm going to do for this question is I'm going to write down the law of the conservation of linear momentum, and then we're going to change some of the words and you'll see how similar the two conservation laws are. So the conservation of linear momentum. So there's our conservation of linear momentum. The first thing that we're going to change is the word linear to angular because we're now dealing with rotation rather than translation. So we're going to change the word force to torque. And there you have it. With those two changes, those two word swaps, we end up with the law of conservation of angular momentum. The total mass of the satellite is 390 kilograms, and the solar panels each have a mass of 16 kilograms. State what is meant by the moment of inertia and explain why extending the solar panels changes the moment of inertia of the satellite by a large factor. So the first thing that we want to say is that this body, whatever we're dealing with, consists of infinitely small point masses, which are all at different radii from the axis of rotation. And the equation that we use to calculate those moments of inertia of those individual point masses is I is equal to mr squared, where I is the moment of inertia, m is the mass, and r is the radius. So that's the first point that we're going to write down. So there's our first mark. Moment of inertia is the sum of every mr squared, so m times r squared, for each point mass m the body consists of at a radius of r. So the next thing to say is starting to link that concept of moment of inertia to what's actually happening with that satellite. Now we're extending the panels outwards, which means we're moving some of the mass to a larger radius. So as you can see from that expression mr squared, if r is larger, then the value of mr squared will be larger, and then so will I. So we're moving that mass to a larger radius, that's our second mark. And then the last thing to say is the fact that that increase in r will give an increase in moment of inertia, but you'll notice that it says by a large factor. Now they're very specific about that for a reason, and that's because we're squaring the value of radius. So a small change in r will give a big change in I. And that's going to be our third mark. Because we're squaring r, a small r increase gives a large I increase. Calculates the angular momentum of the satellite when it is rotating at 5.2 radians per second with the solar panels folded. State an appropriate unit for your answer. Let's first of all write down that 5.2 as the angular speed or angular velocity, which we use the symbol omega for. Now to calculate angular momentum, which we use the letter L, we're going to multiply the angular mass, which we call the moment of inertia, by the angular velocity. So we should end up with I multiplied by omega. So the linear equivalent of that equation would be linear momentum is equal to mass multiplied by linear velocity. Now you remember that the moment of inertia of the satellite when the panels are folded in is 110 kilogram meters squared. So we just need to multiply 110 by 5.2, and that will give us our answer. So that's going to be 572 exactly. Now there are several options that you can choose for your units. You can say Newton meter seconds, you can say kilogram meter squared per second, or you can say kilogram meter squared radians per second. That's the one that I would personally go for, because then that incorporates the full unit of angular velocity as well. But I'll just write down the other two units that you could have. So in terms of marks for this question, you'll get your first mark for correctly calculating the value of angular momentum, which you can only get by multiplying the two correctly substituted values together. And then your second mark will obviously be for the units. Calculate the angular speed of the satellite after the solar panels have been fully extended. So angular speed, angular velocity, doesn't matter. We're trying to find this value of omega. Now remember we said that L is equal to I times omega, and that's labelled in the previous part of the question. But if we rearrange to make omega the subject, so remember that angular momentum is going to be conserved from the previous part of the question, so L is actually going to be the same, and that was 572 kilogram meters squared radians per second. Now referring back to the earlier part of the question, you'll remember that when the panels are extended, the satellite has a moment of inertia of 230 kilogram meters squared. So by dividing 572 by 230, we should get our answer, and the unit is already provided for us this time. So we end up with 2.48696 radians per second. I'm going to round that to 2.49, so to 3 significant figures, because the values given to us in this calculation are also to 3 significant figures. Technically, the 230 could be to 2 significant figures, but if it were to 3, that's how it would be written. So in terms of marks, the first mark will be for correctly substituting the values into the equation. It doesn't matter if it's rearranged and then substituted. You're essentially doing the same thing, but you're doing the steps in a different order. And then the second mark of the 2 will be for correctly getting 2.49. So nice, easy 2 marks there. Figure 3 shows an experiment to determine the moment of inertia of a bicycle wheel. One end of a length of strong thread is attached to the tyre. The thread is wrapped around the wheel and a 0.2 kilogram mass is attached to the free end. The wheel is held so that the mass is at a height of 1.5 meters above the floor. The wheel is released and the time taken for the mass to reach the floor is measured. And then you've got this diagram which shows what that text just describes. State the energy transfers that take place from the moment the wheel is released until the mass hits the floor. So the first thing to say is that this mass, where it's decreasing in altitude, is traveling 1.5 meters towards the floor, is going to decrease in gravitational potential energy. Now you don't get a mark for this point. You actually need to elaborate on where that energy goes. So let's look at what effect that is actually having on the bike wheel. It's causing that wheel to rotate. The wheel is speeding up, it's gaining rotational kinetic energy. The thing to bear in mind though is that there is friction in the joints on the wheel or in the bearing, and there's also air resistance around that system. So not only is the rotational kinetic energy of the wheel increasing, but the internal energy of the bike and the air around it is increasing also. Now, one thing to be very careful of here is that the mass is falling down to the ground, but it's also increasing in speed itself. So the mass is gaining linear kinetic energy. So your first mark is going to be for mentioning those 2 forms of kinetic energy. And then your second mark is going to be for mentioning the internal energy increases due to air resistance and friction. And that's going to be your second mark. Calculations based on the measurements made show that at the instant the mass hits the floor, the speed of the mass is 2.22 meters per second. The wheel is rotating at 6.73 radians per second, and the wheel has turned through an angle of 4.55 radians from the point of release. A separate experiment shows that a constant frictional torque of 7.5 times 10 to the minus 3 Newton meters acts on the wheel when it's rotating. By considering the energy changes in the system, show that the moment of inertia of the wheel about its axis is approximately 0.1 kilogram meters squared. Now, because this is a show that question, it allows us to check our answer and know that we're working towards the correct thing. And therefore, if we don't get that 0.1, we can place extra focus on this question and return to it later in the paper if we need to. So the first thing that we want to do is link these points to the equations that they relate to. So in terms of speed, we're going to be dealing with kinetic energy is equal to 1/2 times mass times velocity squared, or times speed squared. I'm not going to label it here because we're going to run out of space. The rotational kinetic energy is equal to 1/2 times the moment of inertia times the angular speed squared. Notice how similar that equation is to the linear kinetic energy, or translational kinetic energy. And finally, the work done against friction, or the work done by friction, is equal to the torque, the frictional torque, multiplied by the angle over which that torque is exerted. And we're actually given both of those in the question. So let's write down the equation that's going to tie all of this together. We're going to use a conservation of energy. Effectively, that change in gravitational potential energy that we looked at in the previous part of the question, that's going to be distributed between these three types of energy. So change in linear kinetic energy, change in rotational kinetic energy, and work done against friction. So let's just label that equation quickly. So let's break each of these expressions down into their constituent symbols. Now we have two options here. One thing that we can do is substitute the values into this equation as it is and then rearrange to find the value that we don't know, or the value that we're trying to prove, so the moment of inertia of the wheel. Or we can rearrange the entire equation straight away in terms of symbols and then substitute the values in and do a nice simple calculation at the end. I'm going to do the latter, so I'm going to make I the subject of this entire equation. So now all we need to do is substitute the values into the equation. And then it's just a case of putting all of those values into a calculator and getting an answer at the end. So we should end up with 0.107 kilogram meters squared, which, as you can see, if we round to one significant figure, is approximately 0.1 kilogram meters squared. So this is a 3-mark question. The way this is going to work is if you've correctly substituted your values in for gravitational potential energy, change in linear kinetic energy, and work done against friction, then you will get 1 mark. A 2nd mark will be given if you correctly substitute gravitational potential energy or linear kinetic energy. So actually, by making the substitutions for the 3 that I just mentioned, you get 2 marks. So 1 mark for either gravitational potential energy or linear kinetic, but 2 marks for gravitational potential, linear kinetic, and work done against friction. Your 3rd mark will be for making the calculation in the correct format at the end. Now the mark scheme says leading to I is equal to 2.413 divided by 22.6. That's effectively what this calculation is here. If you look at the top half of the fraction, it's going to amount to 2.413, and the bottom half is going to amount to 22.6. Notice how you don't actually get a mark for getting 0.107 at the end, because it's a show that question. So 3 marks there. When the mass hits the floor, the thread is released from the wheel. Calculate the angle turned through by the wheel before it comes to rest after the thread is released. Now the place to start when picturing something like this is with a linear system where an object moving with a certain speed is subjected to friction or air resistance, and it gradually slows down and comes to a stop. Well, this spinning wheel is doing the same thing, but it's just rotational. So instead of using equations like force equals mass times acceleration, we use the angular equivalent, which is going to be torque is equal to moment of inertia multiplied by angular acceleration. Now what we can do here is write down an angular version of a Suvat equation. So v squared equals u squared plus 2as. Final velocity squared is equal to initial velocity squared plus 2 times acceleration times displacement. The angular equivalent of that will be final angular velocity squared is equal to initial angular velocity squared plus 2 times angular acceleration times angular displacement. Now remember, this value of theta, this angle turned, is what we want to calculate. So what we're going to do is substitute the torque is equal to moment of inertia times angular acceleration equation into this angular Suvat equation using this alpha. So instead of saying alpha, we're going to say t divided by I. Now what we need to do is rearrange to make theta the subject Now bear in mind that the wheel comes to rest, so its final angular velocity is going to be 0. I'll use the space below to make that calculation. So we're taking this initial angular velocity of 6.73 radians per second, we're squaring it, we're doing the negative of that, and then we're dividing it by 2 times 7.5 times 10 to the minus 3 Newton meters, which was the frictional torque, divided by 0.107 kilogram meters squared, which was the moment of inertia that we calculated before. Now you might be wondering what we're going to do with this minus, because we're going to end up with a negative angle. Well, this is all to do with the vector nature of these velocities. Actually, because the torque is slowing down the wheel, we could treat that as negative if the velocities are in a positive direction. So actually the minuses would cancel. So our final answer is going to be 323 radians. It's technically 323.089 radians, but we're rounding to 3 significant figures because the values that were given to calculate this answer are all to 3 significant figures, so we need to keep that consistent. Now this is a 2-mark question. The first mark will be for correctly calculating the angular acceleration. Technically just making that substitution of angular acceleration into that angular suvat will get you that first mark. It's recognition of the use of that equation. The second mark is going to be for getting the correct answer. There is an alternative method to doing this question. You can use the rotational kinetic energy that we used in the previous question. Using the conservation of energy, we can say that the rotational kinetic energy of the wheel eventually will entirely be turned into internal energy of the surroundings. So it's going to be equal to the work done against the frictional torque. That may even be a simpler way of doing the calculation. You can see the similarities there, where we're squaring the initial angular velocity, the 6.73. You've got the factor of 2 in there. You've got the moment of inertia, you've got the torque. You're effectively doing the same calculation, but you're just using a different line of reasoning to get there. So this alternative method uses energy, whereas we've used kinematic equations and Newton's second law in angular form. So 2 marks there. A single cylinder air motor running on compressed air has the theoretical indicator diagram shown in figure 4. And we've got figure 4 here, pressure against volume with points A, B, C, D and E making up that shape. From B to C, the high pressure air pushes a piston down a cylinder doing work. At C, a valve cuts off the supply of air and the air in the motor expands adiabatically to D, pushing the piston further down the cylinder. At D, an exhaust valve opens and from D to E to A, the air is exhausted to the surrounding atmosphere as the piston moves up the cylinder. At A, the exhaust valve closes and the inlet valve opens, connecting the cylinder to the supply of compressed air. Use the first law of thermodynamics to explain why the temperature falls during the adiabatic change between C and D. Now to start this question off, let's write down exactly what the first law of thermodynamics is. So delta U is equal to Q minus W. Let's just write down what each of those symbols means. So U is internal energy, Q is heat transferred. It doesn't matter whether it's heat in or heat out because, as we'll discover in a minute, it's equal to 0. And W is work done by the system. Now because Q is equal to 0, we can remove it from the equation, leaving just delta U and W. So it's an adiabatic process, so no heat change. Now because the amount of air is expanding in volume, it must be doing work. So W is going to be positive. Now because of that minus sign, if W is positive, delta U is going to be negative, which means that the internal energy is going to decrease. And then the last thing to say is that if the internal energy is decreasing, then the temperature will also increase because they are directly related to each other. So you'll notice I've made 3 points there. Each of those is worth a mark, so 3 marks. In practice, the cutoff point C can be altered without changing points A, B and E. Figure 5 shows the theoretical indicator diagram of the motor when the air is admitted for the complete stroke. so that the inlet valve opens at A and closes at X. The exhaust valve opens at X and closes at A. So the first thing that we can say about this diagram is that from A to X, we're talking about an inlet. From X to A, we're talking about an outlet. That's going to be useful later. Compare figures 4 and 5 and discuss the effect this change has on the operation of the motor, assuming that it continues to run at about the same speed and with air at the same pressure. You should include in your answer how the change affects, and then we've got the rate of consumption of air, the output torque and power, and the overall efficiency. Now for this 6-mark question, what we ought to do is separate our answer into those 3 sections and talk about each one in turn. It won't be as simple as 2 marks for each point, i.e. 6 divided by 3, because there's going to be a mark for quality of written communication. So that already takes the number of marks available for the content down to 5. But we'll examine marks at the end. Now the first thing to talk about is the rate of consumption of air. Let's first look at the initial diagram. So the higher the power of this system on inlets, the more air is going to be consumed. They're directly related to each other. So we can indicate the power and also the energy by the area under the graph. Now you'll notice on inlets, the area is going to be a lot smaller. It's the area under the line B to C. However, what you'll notice on the other diagram is that B doesn't stop at this point C, it moves right away across to the other side of the rectangle, level with points D and E. So actually, it extends the area to approximately double. So you can see we've got 2 of that area if we extend all the way to X. Now, if we're doubling that area, then we're going to have double the power of inputs and therefore double the air consumption. So let's put that into words. Air enters from A to C on figure 4, but A to X on figure 5. Let's talk about the area. So we're doubling the energy because the area under the graph during that region doubles. Energy is proportional to power. So the power is going to double, and the last point in this section is going to be to say that the air consumption is approximately doubled. So that's sufficient information for the first section on rate of consumption of air. For the output, torque and power section, we actually need to refer back to the area again. However, this time it's going to be during the output section, so from X to A. As you can see in figure 5, the area of this diagram is greater because we've no longer got this curved section near where X is being cut off from the diagram. The area is bigger by roughly 25%. So if we're increasing the area by about 25% because we've no longer got that corner cut off, the output power is also going to be about 25% bigger, because remember the area is an indication of the energy or the work. Now the other thing to say is that the average pressure is going to be greater. As you can see from this diagram, the graph spends more time up near the top than it does lower down, because in figure 4, a lot more of this graph is kind of swooping down to low pressure. So the average pressure in figure 5 is higher than the average pressure in figure 4. And what that then means for our piston is that a higher torque will be exerted, because a higher pressure means a larger force means larger torque. Force is the thing that links the pressure and the torque together. Now thinking about equations for power, if we first of all say that power is equal to force times velocity, that's not the equation that we're going to need, but it's the one that we can use to get to the equation that we will need. That's the linear equivalent. Let's write down the angular equivalent. So torque being the angular equivalent of force, and angular velocity being the angular equivalent of linear velocity. So by holding the angular velocity the same, because as you can see it runs at the same speed, which is important, increasing the torque will then mean that the output power is going to be greater. But that only works if angular velocity remains the same. So that's everything that we need for output torque and power. For efficiency, let's first of all write down the equation. We're not going to write it in terms of energy, but we're going to write it in terms of power instead, because they're proportional. So efficiency is equal to useful output power divided by total input power. Now remember, what we're doing is we are increasing the output power by about 25%, so not too much. However, we're doubling the total input power. So let's write down what that mathematical change is going to do. So removing both of those multiplications off of the front and making them into a fraction, we can see that it's bottom heavy. So actually the efficiency is going to decrease. Because that fraction is less than 1, it's bottom heavy. So that's sufficient information for the efficiency section. Now let's not forget that you'll get a mark for the quality of your written communication. So that's your spelling and your grammar and how legible your text is. And then, as I said before, the other 5 marks are going to be for your content. Now, to get 4 or 5 marks, you need to have covered all 3 sections in enough detail as I've done here. It's likely that missing 1 or 2 bullet points from a given section will lose you a mark, because then that section is considered incomplete. Missing a section entirely would lose 2 marks, but that then scales all the way down to the point where if you're partially covering one section with little or no information about the other 2, then you'll only get 1 mark for your content, so a maximum of 2 marks if you're including QWC. The information is in detail on the mark scheme. Figure 6 shows the actual indicator diagram for the air motor. We've got pressure against volume again, however this curve is a bit smoother and it doesn't have the A, B, C, D, E, X markings. The motor was running at 20 cycles per second when the indicator diagram was recorded. Determine the indicated power of the motor. Now, as we saw before, the work done is going to be indicated by the area of this graph. So we're interested in the area enclosed within this loop. Now, there are 2 ways that you can do this. You can either count the number of small squares or the number of big squares. I would advise counting the number of big squares because bear in mind you're only given 4 marks for this question. So the assumption is it should take about 4 minutes. And I wouldn't really want to be counting to 641 during that time. So by small squares, I mean the smallest divisions in that area. And by big squares, I mean a section that's 25 times the size of a small square. So 5 by 5. What you need to bear in mind is that those areas have different energy values, and we find those by multiplying their width by their height, a volume change by a pressure change. So a small square is going to be 0.1 joules, and that's because we're doing 5 times 10 to the minus 6 meters cubed in width multiplied by 2 times 10 to the 4 pascals in height. And then for the larger square, it's 25 times this because there are 25 of those squares. So just make sure whichever square you're using, you're multiplying that energy by how many squares there are. Now, the first point to make is that the work done is indicated by the area. What we then want to do is write down how many squares we've counted. As I said before, I'm going to stick with 27 big squares. So just making it clear to the examiner what we're doing at each point, not just counting the squares, but we're writing down that we have counted them. What that will then mean is if we've got 27 lots of 2.5 joules, that should bring us to 67.5 joules. Now, because people's methods of finding the area will be different, some people might not even use squares, they might separate this shape into strips, each with a given area. The mark scheme allows you to get an answer between 59 and 69, so 64 plus or minus 5. So our answer is well within that range. And then the last thing to do is to bear in mind that this is running at 20 cycles per second. Now, this is where you could lose your 4th mark. We're given the energy, but we want to find the power, so we want the energy per second. If this is happening 20 times per second, we're getting 20 lots of this energy every second. Now I put seconds to the minus 1 on that 20 because cycles isn't really a unit, so it's just 20 seconds to the minus 1, it's per seconds. Multiplying those together, and that gives us 1,350 watts or 1,350 joules per second. Now, because the mark scheme allows the area that you find to be within a range of values, the same will apply to the power that you obtain. That will also be within a range. Now, presumably, if the energy that you find can be within plus or minus 5 joules, if we scale that 5 joules up 20 times, it's going to be plus or minus 100. And the answer given in the mark scheme is 1,280. So as long as our answer is less than 1,380, we'll be fine. And as you can see, 1,350 is within that range. So 4 marks there. Explain why the indicated power for the air motor is different from the output power. Now this question is just about energy changes which aren't taken into account, the main one being the friction that occurs within the system. It's not enough just to mention the word friction, you actually have to say where that friction occurs. It's only 1 mark, so a very straightforward answer that we can put. Now that would probably be enough to get you 1 mark, but just to be absolutely sure, let's talk about the energy loss or power. So just a 1 mark question, 1 point made. A company claims to be able to provide a combined heat and power plant for a market garden that requires both electrical power and space heating for greenhouses. The engine-driven generator will operate between temperatures of 1450 Kelvin and 310 Kelvin. Show that the maximum theoretical efficiency of any heat engine operating between temperatures of 1450 Kelvin and 310 Kelvin is about 80%. This question is very straightforward because it just uses one equation to make a calculation and obtain 1 mark. So let's write that equation down first of all. So maximum theoretical efficiency is equal to TH minus TC divided by TH, where TH is the temperature of the source and TC is the temperature of the sink. So we just need to substitute in our values. So 1450 minus 310, then we're dividing that by TH again, which is 1450. So that's going to be 1140 divided by 1450. That's going to give us 0.79, which is going to be 79%. Now that should be enough, but it's always worth relating that to the 80% that it gives you in the question. So it's approximately equal to 80%. It can be rounded to that, and then that's our answer. That's our mark. Remember, this mark is for use of the equation, not for the answer that you get at the end. The company makes the following 2 claims about the performance of the plant. Claim 1. When consuming biogas of calorific value 55.5 megajoules per meter cubed at the rate of 5 times 10 to the minus 3 meters cubed per second, the electrical power output will be 210 kilowatts. And then for claim 2, at the same time, the engine will provide heating for greenhouses at the rate of at least 55 kilowatts. Now let's look at claim 1 first of all. You'll notice that the electrical power output is going to be 210 kilowatts. If we can work out the electrical power inputs from the other values that were given, we could find the efficiency and then compare it to the maximum theoretical efficiency that we worked out in the earlier part of the question to see if this value is going to be realistic. So by multiplying the 55.5 megajoules per meter cubed by the 5 times 10 to the minus 3 meters cubed per second, we will end up with a value that is in megajoules per second, or megawatts. You'll notice that the meters cubed cancels with the meters to the minus 3, so that's going to give us 0.278 megawatts, which is going to be 278 kilowatts. And making that calculation will give us our first mark. So by dividing the useful power output, the 210 kilowatts, by the total power input, 278 kilowatts, we can find the efficiency that they're proposing. So that gives us an efficiency of 76%, which is probably a bit too close to the maximum theoretical efficiency. So this claim isn't justified. And then by making that assessment, we gain our third mark. You could also use the efficiency equation in a different way by combining this power input that we've calculated with the maximum theoretical efficiency. We could work out what the power output would need to be for it to run at the maximum theoretical efficiency, but the information that we've written here is fine. Now looking at claim 2, if we look at the difference between the input power and the output power, this is going to be the amount of wasted power, 68 kilowatts. Now claim 2 is suggesting that there'll be a wasted power of 55 kilowatts, which is going to be perfectly plausible because it's within that 68 kilowatts allowance. and then that's going to be another mark. If you wanted to, you could mention that if the efficiency is any lower than the maximum theoretical, i.e. 79%, the output power is going to be more than 68 kilowatts. So 55 kilowatts is perfectly reasonable. Now, ignoring the 2 points that I've written in purple, there are 5 points which are given marks in this answer. So those are the 5 points you need for this question. But some of them could be swapped out for the points that I've made in purple.